This is the next video in my series of videos on Georg Cantor's contributions to the founding of the theory of transfinite numbers. In this video there's going to be quite a significant change in focus from the aggregates and the general aggregates that we've been looking at in previous videos. Now we're going to be looking at ordinal numbers, and rather than aggregates of ordinal numbers such as the first number class and the second number class in general, we're going to be looking at specific kinds of number from those classes and investigating their properties. So the theorems that we're going to be developing and proving in this video and the next couple of videos that I've got planned are going to be focused really on the characteristic properties of specific kinds of specific varieties of numbers from this second number class, as opposed to looking at aggregates of ordinal numbers. So the first kind of number that we're going to focus on is the kind of class of numbers from that second number class that are algebraic functions of finite degree of omega. Remember, omega is itself an ordinal number. In fact, it's the smallest ordinal number of the second number class. So numbers, such numbers will have a representation such as this that's written on the board here. So phi is our number from the second number class, and so we've got omega to the power of mu, nu naught, plus omega to the power of mu minus 1, nu 1, and the power of omega decreases each time until we get down to here, which is nu mu. And there's a couple of conditions that we just need to impose on this, namely that mu we require to be finite, hence it's an algebraic function of finite degree in omega. And these numbers, nu naught, nu 1, nu mu, which we'll call coefficients, I guess, we need those to be finite as well, possibly equal to 0, with the one exception of this nu naught, which we require to be non-zero. Still finite, but non-zero, so that we don't get some kind of degenerate algebraic function of degree mu. We want it to be a definite algebraic function of degree mu. Okay, an interesting observation to make regarding these is that if this nu mu on the end, if it's non-zero, so it's finite but it's non-zero, then the number that we've got here, phi, is going to be a number of the first kind. So in a previous video I've mentioned numbers of the first kind and numbers of the second kind, and the way they're classified depends how they're obtained. Well, numbers of the first kind, if you remember, are obtained from a previous number, a definite previous number, just by adding 1. Well, that's the case here. If this is non-zero, finite but non-zero, then there is a definite previous number that we can add 1 to get to this number here. So it's a number of the first kind. On the other hand, if this is equal to 0, then what we're going to be left with is effectively something that looks like that. So everything, so phi, except for that last term there, that's going to be a number of the second kind, because the only way that I can obtain such a number, particularly in the second number class, is by taking a fundamental series that has that number as its limit. There's no way that I can just take a number and repeatedly add 1 to get to this number here. It's just not possible for me to do that. So there is a distinction there between the two different forms. What we really want to show first of all is that such a representation is unique when it exists. So not all numbers of the second number class will have such a representation, but the ones that do, we want to show that that representation is actually unique. So that's the first thing that I'm going to show in this video. So let's choose another number now from this second number class, psi, such that psi is equal to omega lambda rho naught plus omega lambda minus 1 rho 1 plus omega rho lambda minus 1 plus rho lambda. And to make sure that this is also a non-degenerate algebraic function of finite degree in omega. We're going to put some impose some similar conditions on this expression as we did on the first expression, namely that lambda is going to be finite, and these, let's call them coefficients, rho naught, rho 1 up to rho lambda, are all going to be finite and possibly equal to 0, with the one exception of rho naught. We don't want rho naught to be equal to 0, so it's got to be finite but non-zero. Okay, so what we're going to do is we're going to investigate what happens if the degree of phi is less than the degree of psi. Okay, so we're aiming towards showing that the representation of a number in such a form is unique. So we're going to look now if numbers can differ, if their representations can differ, can we show that the numbers must actually be different as well? The only way that they can be equal is if there's complete agreement with the powers and each of the corresponding coefficients as well. So let's one way that these could differ is in their degree. So we could have, for example, that mu is less than lambda. So let's have a look what happens if we calculate now phi plus psi. So phi plus psi is equal to omega to the power of mu nu naught. I'm not going to write out all of the terms because I don't really need to. Nu mu plus omega to the power of lambda rho naught plus up to rho lambda. Okay, and now just taking a little bit of a side step, then if we've got something like omega to the power of sigma, and let's say we've got, I don't know, tau sigma plus omega to the power of sigma primed, tau sigma primed. So we've got two terms, powers of omega along with their coefficients, and notice that the coefficients are always on the right hand side in these expressions of the power of omega. So I'll explain that in a second, why it's necessary to write the coefficients on the right hand side and not where we typically expect to see them kind of on the left hand side. I'll come to that in a second. Let's just assume, for sake of argument, that sigma is strictly less than sigma prime. So sigma and sigma primes, we're going to be assuming they're finite, but that sigma is strictly less than sigma primed. Well, in that case, using distributivity, we get that this is equal to omega to the power of sigma tau sigma plus omega sigma primed minus sigma tau sub sigma primed. So the laws of indices are valid here because these are just finite numbers. So if we're working with transfinite numbers in the index, then we couldn't guarantee that the usual laws of indices would hold. And in fact, this is something that we're going to come on to in a later video, finding laws of indices that are valid for transfinite numbers as well. But because we're just dealing with finite powers here, then everything just works as normal. So in a previous video, I've shown that such an expression here is just going to be equal to omega sigma primed minus sigma tau sigma primed. So what I end up with is omega sigma multiplied by this thing, which is just equal to omega sigma primed tau sigma primed. So what's the significance here? Well, as you can see, if we've got two terms, two powers of omega, and the lesser power is on the left hand side, and it's followed by a greater power of omega, then that lesser power, effectively, we can ignore it. It disappears. It gets absorbed into this, who knows what, but it disappears. It's not there. But this term is exactly what we've got here. Okay? And we can use this in our expression here because all of these terms are of lesser degree than this term here. So using this, what I've shown here, all of these will go. We can ignore them all. So what I end up with is that phi plus psi just equals psi. Okay, so from this I can deduce that phi is going to be less than psi, because I've got to add something to phi to make it equal to psi. In fact, I've got to add psi itself to phi to get psi in this case. So phi is going to be less than psi. What's the importance of writing the coefficient on the right hand side? Well, it's this. If I were to write this, for example, as rho naught omega to the power of lambda, in a previous video I've also shown that nu naught times omega is just equal to omega. Well, this applies to powers of omega as well, so omega lambda, so that's what we've got here. So this would just be equal to omega lambda, and therefore if I were to write the coefficients on the left hand side, they'd effectively just get absorbed into this power of omega. Whereas if I put them on the right hand side, that doesn't happen. Remember, with ordinal numbers we don't have commutativity of ordinal numbers in general. So this is a different number to this thing here. And we've always got to bear that in mind. We can't just willy-nilly shuffle numbers around, these ordinal numbers, however we want to do so. Okay, so this shows then that if the degrees of these two numbers are different, then the one with the lesser degree is the smaller number. That's what we see here. Okay. So now let's have a look at the case when mu is equal to lambda. So there's what we're going to assume here is that there is some value sigma such that nu sigma is less than rho sigma. So there's some index. As we go along the corresponding powers, we've got them all kind of lined up, one corresponding one atop the other. We go along and they all match up until we get to a certain sigma where there's a difference, and one is less than the other. So for sigma, I less than sigma, and sigma has to itself be less than or equal to mu or lambda. It doesn't really matter which one I say, mu. Then we have nu I is equal to rho I. So obviously this is for wherever this makes sense, because it might be that sigma is actually equal to 0, for example, in which case we don't have a minus 1, a rho minus 1 or a nu minus 1. So to put it into context, it might be that nu naught and rho naught are equal at the first differing coefficients, corresponding coefficients, in which case this really doesn't apply. We don't need to pay any attention to this. But as soon as sigma is 1 or greater, then we've got some of the coefficients are going to be equal to each other. So there's a certain agreement with the terms up until we get to this this sigma term. Okay, so now let's have a look. If we've got sigma, phi, so omega mu, nu naught plus, again I'm not going to write out all of the terms here, plus omega mu minus sigma nu sigma, plus omega mu minus sigma minus 1 nu sigma plus 1, plus nu mu, and to the, so this is phi. This is phi. This number here. It's just I've added an extra couple of terms in here in the expression because they're going to be useful to us. And to this I'm going to add omega mu minus sigma rho sigma minus nu sigma plus omega mu minus sigma minus 1 rho sigma plus 1, and finally right on, just tagged on the end, I'm going to get the rho mu. Okay, so it's quite a long expression, but what we observe is that all of these terms here are followed by terms of higher degree, namely this term here. So all of these from here onwards I can ignore. So for the same reasoning really that I was able to ignore these terms here. Okay, and now let's focus our attention just on this little bit here. So this is a little aside calculation. So omega mu minus sigma nu sigma plus omega mu minus sigma rho sigma minus nu sigma. So this is equal to, using distributivity, omega mu minus sigma nu sigma plus rho sigma minus nu sigma. But this here is just equal to rho sigma. So this is something that was shown in a previous video. So what I end up with here is omega mu minus sigma rho sigma. Okay, so what that means is that this term and this term added together are just going to give me this. So if I just get rid of that now, in fact no, I'll leave it there. So this is therefore going to be equal to omega mu nu naught plus omega mu minus sigma rho sigma plus omega mu minus sigma minus 1 rho sigma plus 1, then continue to rho mu. Okay, now mu is equal to lambda, so wherever I see mu in here I'm going to just change it to lambda. So there's no harm in me doing that. I'm not changing anything in any significant way. So lambda, 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 lambda. And also I know that this nu naught, except for the case where nu naught is less than sigma than rho naught, then nu naught is typically going to be equal to rho naught. So what I'm going to do is I'm going to replace the nu naught with rho naught, and I replace nu 1 with rho 1 and nu 2 with rho 2 up to the one preceding this term here, which is going to be sigma minus 1. So I'd go up to nu sigma minus 1 and replace that with rho sigma minus 1. So notice then what I've got here, it's just the expression for psi. All of the terms match up. So in other words, if I've got mu is equal to lambda and all of this, these conditions apply, then I've got to add something to phi to get psi. Well, that means then that phi must be less than psi. If I've got to add something to phi to get psi, then phi must be less than psi itself. Okay? So what this shows is that the only way that I can have complete agreement between phi and psi, that they can represent the same number, is if the degrees are the same, and all of the corresponding coefficients of each power of omega match up in each expression as well, because this covers the case when the degrees are different. This covers the case where the degrees are different, but we've got a different pair of coefficients at some point along the expression. So the only way that we can get complete agreement is if the degrees are exactly the same and all of the corresponding coefficients are exactly the same as well. So next we're going to move on to addition of ordinal numbers of this type. Okay, so let's have a look at addition of these algebraic functions of finite degree in omega. So there's three cases that we need to consider here. The first case is if the degree of phi is less than the degree of psi. Second case is when the degrees are equal. And the third case is when the degree of phi is greater than the degree of psi. So let's have a look at the case when mu is less than lambda. So in this case, phi plus psi, this is actually a really straightforward case, because as we've seen in a few minutes ago in this video, all of the terms of phi are of lesser degree than this omega to the power of lambda in psi, so therefore they can all be ignored. So all I end up with is that phi plus psi is just going to be equal to psi in the case that the degree of phi is less than the degree of psi. And now let's have a look if mu is equal to lambda. So again we'll have phi plus psi. Well, this is going to be equal to omega to the power of mu naught plus nu mu plus omega to the power of lambda rho naught up to rho lambda. Okay, so just to make it a little bit make these expressions a bit more kind of compatible with each other, since mu is equal to lambda, I'm going to change all of the mu's to lambdas. Okay, now all of the terms to the right of this term here in phi are all going to be of lesser degree than lambda. So that means that this term here is going to be of greater degree than all of these terms here in phi. So because this is of greater degree and it's on the right hand side, so it follows these terms, all of these disappear. So what I end up with is omega lambda nu naught plus omega lambda rho naught plus rho lambda, which using distributivity is just going to be equal to omega lambda nu naught plus rho naught. I'll write the next term in, so lambda minus 1 rho 1 plus rho lambda. So what we see is that when we add two such expressions together that are of the same finite degree in omega, then it's only this the terms of greatest degree that actually we get the coefficients added together, whereas the rest of the terms come from that second, from the addend. So this is the organs, this is the addend. All of these terms just come directly from the addend, and this initial term here is just the sum of the two initial terms of each of the organd and the addend in this sum. So notice that here the coefficient is not nu 1 plus rho 1, and the last term is not nu lambda plus rho lambda. So this is very different to what we would kind of normally expect if we were dealing with, for example, polynomials. It's a very different behaviour that we're dealing with here. Aside from the fact that with polynomials, we wouldn't have a constant. I mean, remember, this is a specific number, this omega. It's not a variable. So they're not, they might look like polynomials to a certain extent, but they're not polynomials. Okay, so now let's have a look at when mu is greater than lambda. So again, phi, I'm going to need more space I think for this one, so phi plus psi is going to be equal to omega lambda nu naught, and there's going to be some point along this sequence of terms where the power of omega in phi is going to be equal to, sorry, that should be a mu, should be mu, where the power is going to be lambda. Okay, because lambda is less than mu, so if we go down decreasing by 1 each time, then eventually we're going to come to lambda, and the subscript here therefore is going to be, I reckon, mu minus lambda in that case then, I think, plus etc. We get down to nu mu plus psi, which is omega lambda rho naught plus rho lambda. Okay, so once again we get a load of initial cancelling here. So all of the terms that follow this in phi, so all of these terms in here are followed by a term of greater degree in omega, namely this one here. So these all go. So we end up with all of the terms here, omega mu nu naught plus omega lambda nu mu minus lambda plus omega lambda rho naught plus rho lambda. But now these terms can be combined to give omega mu nu naught plus omega, okay, I'll write in the previous terms as well, so it's going to be lambda plus 1 nu mu minus lambda minus 1, maybe, I don't know, let's take it as being that, omega lambda nu mu minus lambda plus rho naught plus the next term, which would be omega lambda minus 1 nu mu minus lambda plus 1 plus sorry, no, that's not right. That's not right. That would be rho 1 plus rho lambda. Oof. Right, so that's a long expression. So what we see here is that these terms here are terms that come directly from the organd, from phi. All of these terms here come from the addend, from psi, and then we've got this kind of crossover term here, which is whether the powers, the power of phi and the power of psi are kind of equal at lambda, then we add the two coefficients together. So again, it's very different behaviour to what we'd normally expect really from if we were thinking about these naively as kind of polynomials. It's very different behaviour, so we really do have to go through this in quite a systematic way. But that deals with all of the cases for addition of these such transfinite numbers. So next we're going to move on to multiplication. So let's have a look now at multiplication of these algebraic functions of finite degree in omega. There's a bit of preliminary stuff that I need to go through just before we get to the full multiplication of phi and psi. What I'm about to show will really show sometimes the how counterintuitively these transfinite numbers can behave, that they're completely different. The behaviour is completely different to what we've come to expect through working with finite numbers, for example. So I'm going to start off with it's going to be extending addition a little bit. So if we start off with phi plus phi, which I could write as phi times 2, and notice I'm writing it as phi times 2 and not 2 times phi. Because 2 times phi, remember we don't have the commutativity. We need to specify whether it's phi times 2 or 2 times phi that we're actually working with. So phi times phi is going to be equal to this plus itself. So what I'm going to see, if I go through that, is I'm going to see omega to the power of mu naught plus nu naught plus omega nu minus 1 nu 1 up to nu mu. So I can write that as omega mu nu naught times 2 plus all the rest of the stuff. Mu minus 1 nu 1 plus plus nu mu. And similarly, if I've got phi times 3, phi plus phi plus phi, I'll get, going through a similar thing, I'll get omega to the power of mu nu naught times 3 plus omega mu minus 1 nu 1 plus nu mu. So it's kind of plain to see that if I extend this to phi times nu for some finite nu, this is going to be equal to, so I'm going to get nu phi, so nu is, remember it's finite here, so I'm going to get omega to the power of mu nu naught times nu plus omega mu minus 1 nu 1 plus nu mu. So in other words, to multiply phi, which is a number of this form, on the right by a finite number, effectively I just multiply that first term of phi by nu. And again, I've got to pay attention to the order of the numbers here. I multiplied on the right, so the nu is going to be on the right of all of this here. Admittedly, I probably could get away with switching these two around with them being finite, but we may as well leave it as it is. There's no point in changing things around just for the sake of it. So that's the first thing that I needed to show. The next thing is what happens if we extend this to the expression phi times omega. So this is fine for all of the finite terms, but now we want to extend it to this smallest transfinite ordinal, omega. So this is going to be equal to omega to the power of mu nu naught plus omega to the power of mu minus 1 nu 1 plus omega minus 1 plus nu mu times omega. Okay, well, in a previous video we've seen already that alpha plus nu naught times omega, where alpha is a number of the second number class, nu naught is a finite number, or a number from the first number class, omega is, well, omega, then this is equal to alpha omega. So this is in one of my previous videos. I didn't prove it, but I did state it in one of my previous videos. So notice that we've got a finite, we've got a number of the second number class here with a finite number tagged on the end, nu mu. So effectively that goes according to this rule. So what I get is omega mu nu naught plus omega mu minus 1 nu 1 plus down to omega nu mu minus 1 times omega. Now using distributivity, I can take omega out on the left hand side. So I get omega omega to the power of mu minus 1 nu naught plus omega mu minus 2 nu 1. So I'm going to get right down at this end, I'm going to get omega nu mu minus 2 plus nu mu minus 1. Close the brackets, omega. And I can do, using associativity, I could write this, I could change the brackets so that it looks more like that. So that's just using associativity, which we know is valid in general. And I can play the same game as I did here. So this is a number of the second number class with a finite bit tagged on the end. Off it goes. So I get omega omega to the power of mu minus 1 nu naught, omega mu minus 2 nu 1. What am I going to get down this end? Well, just omega nu mu minus 2 omega. And I can take omega out again. And using a bit of associativity, it should be another bracket there, associativity, I'm going to end up with omega squared here, omega mu minus 2 nu naught plus omega mu minus 3 nu 1 plus nu minus 2 and omega there. Do exactly the same thing. So I continue this process. What I'm going to end up with right at the very end is something that looks like this. I'm going to get omega, what's it going to be, mu minus 1. Inside the brackets I'm going to be left with omega nu naught and then an omega there. So something that looks like that. Now again, using associativity, I can muddle all the things around. Get omega to the power of mu times nu naught omega. We've seen also in a previous video that this omega naught times nu naught times omega, where nu naught is a finite number, is equal to omega. So it was in the same video as this, and I think I proved this using coherent fundamental series. So this is just equal to omega. So what I end up with is omega to the power of mu plus 1. So this is really significant because it means that if I multiply phi on the right by omega, effectively what emerges from it is just the highest power of omega raised to the next highest power, omega to the power of mu plus 1. All of the coefficients have all been effectively absorbed into this. And that's all that results from the whole thing. I can generalize this as well to, if I've got phi times omega to the power of k, for example, then what I'll end up with is omega to the power of whatever the highest power of omega is in phi, which is mu, plus k. Again, all of the coefficients just disappear. They get absorbed into in all of the arithmetic, all of the manipulation. They all get absorbed. All that emerges is this thing here. So this is going to be a really useful result for us in general. This one and the one here. We're going to be using at various points along the way. So what I'm going to move on to next is actually multiplying phi and psi together now. So this is the general multiplication that we're moving on to next. So we've got the fairly difficult stuff out of the way now for multiplication. It's a pretty straightforward road now to these general results. So we're going to have a look at phi multiplied by psi. We're going to start off by assuming that in psi we've got that rho lambda is actually equal to 0. We'll look at the case when rho lambda is not equal to 0 separately. So in this case, what we're going to get is we're going to get phi times omega lambda rho naught plus omega lambda minus 1 rho 1 plus omega rho lambda minus 1. Remember, we're assuming that this is equal to 0. So that's equal to, using distributivity, phi times omega lambda rho naught plus phi omega lambda minus 1 rho 1 plus phi omega rho lambda minus 1. And then I can use associativity, and I get phi omega lambda rho naught plus phi omega lambda minus 1 rho 1 plus phi omega rho lambda minus 1. But these are just what I've been doing just a couple of minutes ago. Phi times this is going to be omega to the power of mu plus lambda times rho naught plus omega to the power of mu plus lambda minus 1 rho 1 plus omega mu plus 1 rho lambda minus 1. So in the case of rho lambda being equal to 0, then it's simply a case of increase all of the powers of in psi, all of the powers of omega, increase them by mu, and that's all it amounts to. So now let's have a look at the case when rho lambda is not equal to 0. So it's obviously still got to be finite, but it's non-zero. So we've got phi plus psi. So this is again going to be equal to phi omega lambda rho naught plus omega lambda minus 1 rho 1 plus omega rho lambda minus 1 plus rho lambda. So again, using distributivity, we get phi. I'm not going to use it in exactly the same way though, so it's going to be phi times omega lambda rho naught plus omega lambda minus 1 rho 1 omega rho lambda minus 1 plus phi rho lambda. So this is effectively what we've just done up here, all of this. So remember, we assumed here that this was equal to 0, so the whole thing just reduced to that. So this is just going to be what we got here. Omega mu plus lambda rho naught plus omega mu plus 1 rho lambda minus 1. And now this one is just what I did a few minutes ago, phi multiplied on the right by a finite number. So this means that I just multiply the first term of phi by that finite number. So I get omega to the power of mu, nu naught, rho lambda, but then all of the rest of phi stays the same. So I get plus omega to the power of mu minus 1 nu 1 plus down to nu mu. So it's quite a long expression, but that finishes the multiplication in general for these algebraic functions, finite degree in omega. What we're going to move on to next is looking at some resolutions or factorisations of such expressions. Okay, so just to finish off this video, we're going to look at how you can effectively factorise or resolve numbers, these algebraic functions of omega. So we've got a slightly different set of assumptions here. We've still got an algebraic function of omega of finite degree, but what we're going to assume here is that each of the coefficients are fine. They're still finite, but they're all non-zero in this case. So we're stripping out all of the superfluous terms effectively. So each term here it's non-degenerate, and we've got a descending chain of powers, mu, mu1 down to mu tau, decreasing in size. Mu tau could be equal to 0, it's greater than or equal to 0 at worst. Okay, so then let's have a look at the expression omega to the power of mu1 nu1 plus omega to the power of mu tau nu tau multiplied by, on the right, omega to the power of mu minus mu1 nu naught plus 1. So using distributivity, I'm going to get omega mu1 nu1 plus omega mu tau nu tau omega mu minus mu1 nu naught plus this whole thing again, just tagged on the end, which is going to be omega mu1 nu1 plus omega mu tau nu tau. Right, so using associativity here, just saved me writing it out all over again. I'm just going to change the brackets around a little bit. I get that. And then this thing here is what I've just done earlier in the video. So when we had something like phi omega to the power of k, where phi, the degree of phi was mu, then this was just equal to omega mu plus k, for example. Well, I'm going to use that here. So this is effectively my phi in here, although obviously it's not the phi that we've got up here, it's just the phi that representing the phi here, and then I've got the omega, and the k is equal to mu minus mu1. So it's just, all I'm going to get here is omega to the power of mu1 plus mu minus mu1 mu naught plus all of this plus omega mu tau nu tau, but this power here is just equal to mu nu naught plus all of these terms here, omega mu tau nu tau, which is equal to phi. So in other words, this gives me a kind of partial factorization or partial resolution of phi here. So naturally I can continue this because this expression here is essentially of the same form as this. So I've still got the descending powers of omega, and these are all finite non-zero, just as they were before. So I can do the same thing to this here. And if I continue with this, then I can get a full factorization of phi, which is going to be equal to omega to the power of mu tau nu tau, and the first bracket is going to be omega mu tau minus 1 minus mu tau nu tau minus 1 plus 1. The next one, it's going to be omega tau minus 2 minus tau minus 1 nu tau minus 2 plus 1. Continue down, and I get right on the very end omega mu minus mu1 nu naught plus 1. And notice the order of the powers here. So whereas we had up here mu, mu1 to mu tau left to right, they're kind of reversed to a certain extent here. So I've got mu and mu1, and then the powers I can't say that they decrease, but mu tau ends up right on the left hand side over here, whereas mu ends up right on the right hand side. That's just how it is, and it's due to this non-commutativity, really, that we can't just reorder the factors here. So I couldn't just move this to the beginning and this to the end and things like that. The factors come out in this order. That's the order that they have to stay in. But that's not as far as we can go. There is something else that we can do. So using our multiplication that I went through earlier in the video, if we've got, I'll use this as an example here. So if we've got omega mu minus mu1 plus 1 times nu naught, then this is a transfinite number from the second number class in here, multiplied by a finite number on the right. So compare with what I did in the previous one, where it's phi times rho naught, or phi times rho, sorry, and it amounted to just multiplying the first term of phi on the right by this finite number here. So let's do that. My phi is effectively this here. Not obviously, again, not the same phi as this. So what I'm going to get is just multiplying the first term here on the right by this. I get omega mu minus mu1 nu naught plus 1. So in other words, this factor, or this resolver, I don't know what the strict name for it is going to be, I can actually replace with this thing here, and I can do this to all of these. So I get another resolution of phi, which looks like the following: nu tau. So in the first bracket, I'm going to end up with omega mu tau minus 1 minus mu tau plus 1 nu tau minus 1. Then I'm going to get the second bracket, omega mu tau minus 2 minus mu tau minus 1 plus 1 nu tau minus 2, and continue this process. Omega mu minus mu1 plus 1 nu naught. So these factors are irresoluble, so these themselves don't factorize further. So this is a nice, neat factorization of phi. Again, I can't just willy-nilly change the order of the terms. So as tempting as it might be to bring all of the coefficients to the left or to the right or whatever, I can't do that. They've got to stay where they are in between the relevant factors. But that gives me a complete factorization for phi. So does this one. They're both perfectly acceptable. So that brings us to the end of this video. The next video that I'm going to be doing is going to be dealing with exponentiation of these numbers of the second number class. So we're going to look at some effectively laws of indices of when we've got transfinite numbers in the powers as opposed to finite numbers. So I want to thank you for watching this video, and I look forward to seeing you in the next video.